Today we're going to talk about Kawamata-Viehweg vanishing. So this is really the bread and butter vanishing theorem that makes everything else in this field go through, and it's also the reason why we need to work with KLT singularities. So during the proof of this, we'll kind of see where the condition that the discrepancies are strictly bigger than -1 really comes up for this to hold. So let me state, I think in this class, I'm going to state maybe 4 or 5 different versions of Kawamata-Viehweg vanishing, and that's just the beginning of all the variations that there are. So let me just start with the most easy to state one. I'll call it KV1. So let's say X is smooth projective. And throughout today, N will be the dimension of X. And let's say that L is big enough. Cartier divisor. Then KV vanishing tells you that the conclusion of Kodaira vanishing still holds for this L. So HI of KX plus L is 0 for I greater than 0, or equivalently by Serre duality, HI X OX of minus L is 0 for I less than the dimension. Okay, so that's maybe the easiest version to state of Kawamata-Viehweg vanishing. So in this version, it's just you slightly relax the conditions in Kodaira vanishing from ample to big NF. So you could see how that might be a useful statement to have. But even to prove this version, we actually need to talk about a stronger or an a priori stronger version with more assumptions. So let me, or maybe stronger isn't the right word, but we need to talk about several other versions just to prove that version. So let me call this KV2, and you can think of this version as log Kodaira vanishing. Meaning that the statement is exactly what you would get if you look at Kodaira vanishing and replace KX with the log canonical divisor for some log pair. So let X comma delta be a symbol normal crossings pair, but a projective one. So X is projective and delta is an SNC divisor. And if you write delta as some AIDI, let's assume that the AI are between 0 and strictly less than 1. So another way to say this is delta is a boundary, and the pair is both SNC but also KLT. So the coefficients are strictly less than 1. And let's say that L is a Cartier divisor. That's numerically equivalent to a divisor M plus delta, where M is an ample Q Cartier Q divisor. then the conclusion is that vanishing holds for this L. So we can write it as HI of kx plus delta plus m is 0 for I greater than 0. So just a few things to point out here. I wrote it in this way to make it clear how it's the log version of Kodaira vanishing, because it's exactly the statement of Kodaira vanishing, where instead of kx, you have kx plus delta, because m is ample. But also, there's an interesting point that m is just a Q Cartier Q divisor, and delta is also just a Q divisor. I guess the Q Cartier assumption is vacuous because we're on something smooth. But the point is that m and delta themselves don't have to be Cartier. They just have to be numerically equivalent to something Cartier. So really, here I should have really written L, because L is the thing that's actually Cartier, so it makes sense to talk about OX of kx plus L being a line bundle. Okay, and then the Serre-Dual way to write it is just involving L. Okay, so that's KV2. And I want to make a remark here that for this version, we actually don't need strictly less than 1. And that's because the condition of being ample is open. So if I had the same setup, but where some of my AI are equal to 1, so let me write it as a remark. If some AI can go up to 1, then we can just replace delta with a delta prime that's just 1 minus epsilon times delta. And now this satisfies the condition that AI is strictly less than 1. And we can replace m with m prime equals m plus epsilon delta. And now for small epsilon, this is still ample, because being ample is an open. So actually, for KV2, we also get the same conclusion if we allow some of the coefficients to be equal to 1, because it's actually equivalent. Okay. So let me just write the key point is that this is still ample, and that this has coefficients strictly less than 1. Okay, so that's KV2, so log Kodaira vanishing. So the strategy for proving KV2 is to reduce to usual Kodaira vanishing. So we want to have a way to remove these deltas, because we know that the cohomology of m vanishes, of kx plus m vanishes, as long as m is actually an integral divisor. So we want to replace x with this boundary. We want to replace that by something where we just have a Cartier divisor that's given by m. And so this is done by the following proposition. So I should say right now I'm basically just outlining all the various versions and all their logical relations, and then we'll go through and actually prove them. But so this is really the key proposition. If we have x comma delta, a projective S and C pair as above. Actually, for this proposition, we don't even need projective. We definitely need projective in these previous statements because they're statements about global cohomology vanishing, and so for global cohomology to be well behaved, we need projective. But this statement, this statement's fine even without projective. So let's say x comma delta is in S and C pair as above. So with boundary delta and the round down of delta is 0. So that's another way to say that the coefficients are strictly less than 1. And let's say that L, just like above, is a line bundle or a Cartier divisor. Here, yeah, I think I can say numerical. That's equal to M plus delta, where no assumptions on M now. Just if you can write it as M plus delta, then there exists a finite cover in fact, a finite flat cover. I guess I called it P in my notes, so let me do that just to not mess up notation. There exists a finite flat cover P from Z to X such that 1, Z is also smooth. 2, the pullback of M is Cartier. And 3, the cohomology of minus L is the direct summand of the cohomology of minus M on this Z. And so this is really where the condition that the coefficients are strictly less than 1 is used in constructing this P. And now the point is this lets us reduce to a case where we don't have delta anymore. And now whatever property we assumed about M downstairs will be preserved under this pullback because this is a finite map. And so now this proposition will let us reduce to the case where we just want to show vanishing for our M instead of M plus delta. Okay, and then this is really, I think, where the definition of KLT came from. It was really the condition you needed for this proposition to be true so that this argument for vanishing holds. Okay, so that's the main kind of technical proposition. And then now we have the third version, which you can think of as the logarithmic version of KV1. So we saw KV2 was already log Kodaira, and we saw this KV1 that was Kodaira with big NF instead of ample, and now we have a log version of the big NF statement. So let X comma delta be a projective S and C pair. With same assumptions on delta as above. So I won't keep writing delta is equal to sum of AI DI, but that's what the AI are. They're the coefficients of the components of delta. And suppose that L is a Cartier divisor. With L being numerically equivalent to M plus delta for M a big NF. Q divisor, then we have vanishing for KX plus L. And again, the point is that this you should think of as kx plus delta plus m. So that's why it's the big enough version of kv1, because m is big enough. And again, this is Serre dual to the statement that hi x ox minus l equals 0 for I less than n. Okay, so that's the third version, and then there's one more version I want to state before actually getting to the proofs, and that's really the most important one, which is the KLT version. So we're now x delta is not actually smooth anymore, or SNC. So Kawamata-Viehweg 4. Let x comma delta be a projective KLT pair. And let L be a Cartier divisor. That's linearly equivalent to m plus delta, like before, or numerically equivalent to m plus delta, where m is a big enough Q Cartier Q divisor. Now the Q Cartier condition is really a condition because x is singular now. Then the conclusion holds for the cell. Let's outline the strategy. So we start with Kodaira vanishing. And then our key proposition reduces KV2 to Kodaira vanishing, because it lets us remove these deltas, and KV2 was the version where m was ample. So we can reduce this to Kodaira vanishing. Then to get from this ample plus boundary version to KV1, which was the big NF with no boundary version, here we have to use the fact that big NF divisors can be written as ample plus effective. But then we also have to resolve, because we need our effective piece to actually be a simple normal crossings boundary. So here, even though in the statement of KV1 x is smooth, we need to do some kind of log resolution, because our big NF divisor will be ample plus some effective that we don't really have a control over. So here we need resolution. But now we need to understand, how does the cohomology of these adjoint bundles, of these kx plus L type bundles, change when you take a resolution? And for this, along the way, we'll prove a version, an easy version of Grauer-Riemann-Schneider vanishing, which will actually follow from KV2. But which basically tells you how does the cohomology of adjoint bundles change under resolutions. So that gives us KV1, where x is smooth, no boundary, and L is big enough. Then, just like in this first arrow, we apply the proposition to add back in a boundary. So this gives us KV3, where now we have big NF plus boundary. And now, again, we need to do resolutions plus a slightly stronger version of Grauer-Riemann-Schneider, which will follow from KV3, to go from from KV3 to the version for KLT pairs. Okay, so that's roughly the outline, and then the other remark I wanted to make is that in various steps work with using the version where you have HI of -L, and then other steps work better if you use the version where you have HI of K plus L, and then it's really like the arguments just don't work if you use the stair dual formulation of the statement. You really need to go back and forth for the various steps to make the arguments work. Okay, so that's where we're headed. Any questions? Okay, so we're going to start with this proposition. Let me see if I can just copy the statement down. It's kind of long. Okay, so I'll leave the statement here for a second, so we can redigest it before scrolling down, because if I copy it, it's just going to take up the whole screen anyway. Okay, so what we're going to do is we're going to induct on the number of components of delta. So remember, delta is going to be some sum of AI di. So we're going to induct on the components, and we're going to show that there exists some cover like this, where the conclusion is true when you have m plus one less component of delta. Okay, so let me just write it out explicitly. So let's say that we'll start with the first divisor, and since it's rational, we can write it as b over m, where b is less than or equal to m minus 1, greater than or equal to 0. And of course, the case where b is 0 is kind of easy, but the argument doesn't really care about allowing it to be 0. So, okay, so we have this divisor in our delta that's of the form b over m d. And the idea is to find some cover where we can kind of get rid of this denominator m. Because like the easiest thing we can do would be to just say induct on the components of delta and just prove the statement for L minus b over md. But now that's not a Cartier divisor anymore, because we have this rational coefficient. So we need to go back to some cover where we can kind of clear this denominator on our d1, sorry. Okay, so that's our step 1. There exists a map f from x prime to x that's finite flat, with the properties that 1 f upper star of this d1 is equal to m times a divisor d. And so that lets us clear the denominator. 2, the pullback of our delta is still S and C. So maybe I should say first x prime is smooth. And yeah, that's it. So we want to produce a cover that's finite flat that pulls back d1 to be m times some other integral divisor d, and where we still are in the S and C setting. So to do this, basically we can construct this for projective space. So here's here's what we can do for projective space. We just take the map from Pn to Pn. That takes all the coordinates to x0 to the m up to xn to the m. So just take the mth power map on Pn. And now this does the job if D was some generic hyperplane in Pn. But now if D is ample, so let's say D is very ample, D1 is very ample on X, then we get a map X to Pn, whose hyperplane section is this D1. And so up to maybe composing by some automorphism of Pn, we can make it be a generic hyperplane section. And so then if we take the fiber product, we get something smooth. So fiber product satisfies X prime by like Bertini theorem, or by Kleiman-Bertini theorem. And by definition, this map pulls back a hyperplane to be m times a hyperplane, so it'll pull back D1 to be m times whatever the hyperplane of section of X prime is. So okay, so that does the job for very ample divisors. And now for an arbitrary divisor, we write it as the difference of very amples. So and apply to each of these. Okay, so that gives us such a cover. And again, by this Kleiman-Bertini, we get that kind of each of the other divisors are also going to be in generic position up to after applying some automorphisms, and so when they'll also get pulled back to smooth components that still intersect normal crossings. Okay, so that's step one. This lets us clear denominators. Now we want to pick out the cohomology of BD, right? Because now when we pull back, so now what do we have? We have that F upper star B over M D1 is equal to B times D. So now upstairs, we can subtract by BD. So we need to find a way to relate the cohomology of like L minus BD with the cohomology downstairs. So for this step, basically we just say that that because F is finite flat, you have things as a direct summand. So the claim is that HI X comma OX minus L is a direct summand of HI X prime OX prime minus the pullback of L. And the reason is that we're in characteristic 0. So if we look at the map OX to F lower star OY, or OX prime, this is some finite algebra extension in char 0. And so we can split it by taking the trace. So 1 over degree of f times the trace splits. So we get that f lower star ox prime is ox direct sum something called b. And now we can use the projection formula to compute cohomology. So now for any sheaf, we have that f lower star f upper star f is equal to f direct sum some other stuff, where I guess in my notation it's b tensor f, but it doesn't matter so much. And so the cohomology of f is the direct summand of the cohomology of f lower star f upper star f. But this, because f is finite, is the same as the cohomology of the pullback. Okay, so that lets us actually go upstairs, pull everything back, and it suffices to prove the statement on this pullback. Great, but now the issue is that we want to get something about. Let me go back to the statement. We want to get something about cohomology of minus L being related to cohomology of the pullback of just this M piece. And right now what we have is we have a cover where our first divisor becomes Cartier, but we're still looking at cohomology of the pullback of L, not the pullback of M. So we need to subtract off our divisor. So step 3 is to use a cyclic covering trick to be able to subtract off this L, this BD, sorry. And this is where the coefficients being less than 1 comes up. Okay, so we know that this pullback of D1 is a divisor in the linear series of M times D. So we can make a cyclic, we can construct a cyclic cover. Let's call it G from X double prime, which is the cyclic cover, the M-fold cyclic cover branched along D1, or F upper star D1, sorry. So this is some cyclic cover of X prime. And what's the key point of the cyclic cover? It's that G lower star OX prime, double prime, by construction is the direct sum from I equals 0 to M minus 1 of OX prime minus ID. And so now this is going to let us compare the cohomology of something downstairs with the cohomology of a twist by minus BD. Or sorry, the cohomology of something upstairs with the cohomology of twists by minus ID because of this push forward. So let's do that more carefully. So yeah, so HI of X double prime with coefficients in the pullback of OX prime BD minus F upper star L. So recall, this is now the thing where we've subtracted off the first divisor completely, because when we pull back L, we've cleared denominators on D1, and then we just have B times D there. But now we've done BD minus that. So here we only have N minus 1 or whatever R minus 1 divisors in our boundary for this. So this is the thing. This is the thing we can control by induction because we subtracted off the first divisor. Now, by the projection formula, this is equal to the direct sum. So by projection formula plus this formula for G lower star O. Then this is equal to the direct sum of the cohomology downstairs. So now downstairs is x prime of OX prime, but now we have to twist by all these various pieces in the summand for G lower star OX double prime. So we have to twist by minus ID for various I, so we get B minus I D minus F upper star L from I equals 0 to M minus 1. Okay, so this is really the key observation in this whole argument, that taking the cyclic cover lets you manipulate and add these multiples of BD. So are there any questions just about this step? Okay, so now because B is less than or equal to M minus 1, so this is where our assumption on the coefficients comes in, then we see in this direct summand one of the pieces is exactly HI X prime OX minus F upper star L. It's exactly the piece for I equals B, which contains as a direct summand the thing we cared about, which was HIX OX minus L. So now we've produced a cover F composed G from X double prime to X, where the cohomology of OX minus L is a direct summand of the cohomology of this thing. But now we can compute that. So G upper star of F upper star L minus BD. This is going to be, so recall L was M plus delta. So this will be G upper star F upper star M plus the first term gets subtracted off because we cleared denominators and subtracted B. So we just get plus the sum of AI times G upper star F upper star DI, now for I strictly bigger than 1. So we have one less term in our boundary. And also recall that for the cyclic cover, because D1, F upper star D1 is smooth, by step 2, or maybe by step 1, then on the cyclic cover, everything is also smooth in normal crossings. So on X double prime, we have this new divisor delta double prime, which is the sum from I equals 2 to whatever. I don't think I called it anything before, so let me call it R. Of AI, G upper star, F upper star DI, where this is SNC. It satisfies the conditions that the coefficients are less than 1 and greater than or equal to 0. And we have our divisor L double prime, which is this divisor G upper star of F upper star L minus BD. And so now we can apply our inductive hypothesis in this case because we have one less divisor in our boundary. So then there exists some h from z to x double prime, such that the cohomology of minus L double prime is a direct summand of the cohomology on Z of the pullback of just the M piece now. So H upper star, G upper star, F upper star, M. And so taking P to be this composition, from Z to X, because we already know that HIX OX minus L is a summand in there, then we're done. So that produces for us the Z, where the cohomology of minus L is contained in the cohomology of the pullback of minus M. Oh, and I should have said here, so also for free, it kind of fell out that on Z, this pullback of M is Cartier, because well, that was part of our assumption, but that was the whole point here, that once we passed to this X prime, now subtracting off BD still got us something Cartier. So now on this next step, when we subtract something off, we're still Cartier. So every time we subtract off one of these D's by passing to a cover, we still get something Cartier. So in the end, even though M is not necessarily Cartier, M has denominators. When we pull back, all the denominators of M are gone. Great. So that's the I think these are called Kawamata covers. I think developed by Kawamata when first running this proof. So now we can move to actually proving the various versions. Okay, so let's start with KV2. This is the ample. This is the one where you have ample plus a boundary. So x comma delta as before, and L is M plus delta, where M is ample. Then by our proposition, we can find some cover Z to X with the cohomology on X of OX minus L being a summand of the cohomology on Z with coefficients in minus P upper star M. But now, because P is finite, and also, so, yeah. Anyway, because P is finite, then P upper star M is ample. And so this is 0. For I less than the dimension by Kodaira vanishing. Okay, so that was just a straight up application of our proposition. Okay, so now we have log Kodaira vanishing, or KV2. So next we want to use this to prove Kodaira vanishing for big NF. So this Kawamata-Viehweg vanishing 1. So now we don't have a boundary. X is just smooth projective, and L is a big NF Cartier divisor. Okay, so here's an exercise that follows from Kodaira's lemma on big NF divisors. So L is big NF if and only if So the usual statement for big is that something's big if and only if it's ample plus effective. But if you're Neff, you're on the closure of the ample cone by Kleiman's criterion. And so there's a version for big and Neff which says you're ample plus effective such that this exhibits you as the closure of the ample cone. So to be more precise, if and only if there exists an effective n such that L minus 1 over k n is ample for all k large enough. So it's kind of simultaneously combines being in the closure of the ample cone because you're ample plus 1 over k effective for arbitrarily large k, and that you're in the big cone, meaning that you're ample plus effective. Okay, so that's that I'll leave as an exercise. But the key point is that this n is fixed. The ample depends, like if I write this as ak, so that depends on k, but the effective piece is fixed. So now we're going to take a log resolution of this n. And let's call it mu from y to x, and let's write the exceptional locus as these EIs. So now what do we know? So we know that L is Q equivalent to an ample plus 1 over Kn, where again this ample depends on the K, but the N doesn't. And so when we pull back, we get that mu upper star L is Q equivalent to mu upper star A plus 1 over K strict transform plus 1 over K times whatever exceptionals we get when we pull back N. I shouldn't use A because I use that for our boundary and the other pieces. No, actually, maybe that's okay though, because in this statement there is no boundary. So something like this, but the point is that the AIs depend only on N, while I can make the K arbitrarily large. So the AIs might be bigger than 1, but I can just pick K large enough so that AI over K is smaller than 1. And so roughly this will play the role of our boundary. This will play the role of our boundary. The only issue is that we want to apply the previous version, which needed an ample divisor, but here we have mu upper star of an ample. So we have to modify things a tiny bit to replace mu upper star A with an ample divisor on Y. So to do that, we need a version of the negativity lemma that came up before. So this was the lemma that if you have exceptional divisors, then like exceptionals for a birational map intersected with curves that live inside of the exceptionals are always strictly negative. That's the negativity lemma. But another way to phrase that is that mu upper star A minus sum of BI EI is ample for very small BI. Because mu upper star A intersects everything outside of the exceptional locus strictly positive by the projection formula, because I'm pulled back an ample. And it intersects curves that are in the exceptional divisors to be 0, but the negativity lemma tells us that the exceptionals intersect curves inside of them to be strictly negative. And so if we subtract off a very small amount of the exceptionals, then every curve will intersect strictly positive. And so now we just fudge this expansion with these BIs. And so we write mu upper star L is mu upper star A minus sum of BI EI plus 1 over K strict transform of N plus sum AI over K minus BI of the EI. And now with this, let's call this A prime, and or maybe we'll call it AY because it's on Y, and this we'll call delta Y. Now we're in the situation of Kawamata-Viehweg vanishing with ample plus boundary. So yeah, so now by KV2, we know that on Y, we have the vanishing we want. And this is the step where it's actually easier to use the Serre dual statement. So I'll write it that way. So now on Y, we have that omega Y tensor mu upper star of OX twisted by L equals 0 for I greater than 0. But now we want to say something about HIX omega X tensor L. And what we have is something about omega Y tensor the pullback of L. So now this is where we need this Grauert-Riemann-Schneider type vanishing theorem. Are there any questions before we start that? Okay, so let me just start with a lemma. Let's say that mu from Y to X is projective, so of course we'll apply it to this resolution. And let's assume that each of the varieties are actually projective. So let's say mu is a birational map, or it doesn't have to be birational actually. So mu is a morphism between projective varieties, so it's automatically projective. Then the following are equivalent. One, the cohomology on Y of a coherent sheaf twisted by the pullback of a sufficiently ample divisor on X is 0. And 2, the higher direct image of this F is 0 for this particular J. So here we should have J is greater than 0. And then for that same J, this cohomology on Y vanishing is equivalent to this push forward vanishing. This lemma is kind of interesting because the second statement is local. The second statement is about a sheaf. And so this vanishing is true locally on X. But the first statement is really global, because the global cohomology, you only expect this type of vanishing if Y is proper. So the point of, and this is why we need to assume that X and Y are actually projective rather than just the morphism being projective, because we're relating a local condition too with an actually a global condition in one. Okay, so let's write down the proof. So we can write down the Leray spectral sequence for computing the cohomology in one using the projection formula. Because we have a divisor of the form, or a line bundle, sorry, not even line bundle, a coherent sheaf of the form F tensor a pullback, and the projection formula plus Leray spectral sequence will relate it to the cohomologies of some higher direct images downstairs. So our spectral sequence then looks like HA on X of RB mu lower star of F tensor OX of H abuts to HA plus B on Y of F. I'll just write it as F twisted by mu upper star H. Okay, so that's what the Leray spectral sequence plus projection formula looks like. So the point here, the projection formula just tells you that RB mu lower star of the whole F tensor mu upper star term is the same as RB mu lower star of F tensor OX of H, and that's because this OX of H is a line bundle. Okay, so now for H sufficiently ample, we have that this term equals 0 for all A greater than 0 by Serre vanishing. So if I take an H, because this RB mu lower star F is fixed, so if I make H ample enough, then all the higher cohomologies of that will vanish. And so for H sufficiently ample, the spectral sequence degenerates to just give us that H0 to give us that H0 of X RB mu lower star F. Well, let me just write J here. Rj mu lower star F tensor OX of H is equal to Hj of Y with coefficients in F twisted by mu upper star H for H sufficiently ample. And so now we get that the right-hand side is 0, if and only if the left-hand side is 0. But because we're twisting by a large enough ample here, the only way that we have no global sections after twisting by sufficiently ample is if our sheaf is 0, because that's one of the criteria for ampleness, is that when we twist by a large enough ample, we always get global sections. So the right-hand side is 0 for H sufficiently ample. If and only if this push forward is actually the 0 sheaf, because we'll always get global sections otherwise. Okay. Any questions about the lemma? Okay, so now we're going to apply this lemma to get our Grauert-Riemann-Schneider type vanishing. But it really comes from just continuing the argument. We know something about hi y with coefficients in omega y tensor of the pullback. We want to prove something about the analogous line bundle on X. So we want something about sheaves of the form omega x tensor OX of L, but we know about hj y omega y tensor ox oy of mu upper star ox of L. So we want to apply this lemma. So we want to add some ample to our situation. So let's add RH to L. And so when we do that, we still have the vanishing for this HJ. Somehow we've added more positivity. So if we already know that HJ here is 0. And so when we add this some large enough multiple of an ample, we'll still get something 0. So if you want, you can say, well, take a generic section of RH so that all our assumptions are satisfied still in our argument to get the vanishing on Y. So here everything's for j greater than 0. Okay, so we know that these vanish for large enough r, and in fact they also vanish for r equals 0. But now we write things down. So mu upper star L was of the form ample on Y plus boundary on Y. But now when we pull back this ample from the base, I guess I'm giving the argument for Y as before. We still get this vanishing. Okay, so let me not skip that, I guess, because I started. So mu upper star L is like this. So then mu upper star L plus RH is AY plus R mu upper star H plus delta Y. And the point is just that this is still ample because we have ample plus the pullback of an ample. So it's still ample. So I guess this justifies why things still vanish when we twist by RH. And so now we can apply our proposition or our lemma. Right, so now L plus RH for R large is sufficiently ample on X because it's, well, really any divisor plus a large enough multiple of an ample is going to be sufficiently ample, but here we're even better because L is big enough. So by our lemma, because we know the cohomology upstairs of omega y tensor this pullback of a sufficiently ample is 0, then by our lemma, we know that the push forward of omega y is 0. And this is the first version of GR vanishing. Okay, so that was an important statement, but yeah, it's basically applying an earlier version of Kawamata-Viehweg vanishing plus this lemma. And so we get the higher push forwards of the canonical on Y are 0. But in fact, we also know that the 0th push forward of omega y is omega x because x is smooth, and so in particular has canonical singularities. So now this lets us compare cohomology of these adjoint sheaves of these omega y plus stuff on y with the cohomology of omega x plus stuff downstairs. Because now we know that the Leray spectral sequence doesn't contribute any cohomology for omega, and we know that when we push forward, we just get omega x. So now we just write down the cohomology. Or we write down the spectral sequence. So hi x with coefficients in R j mu lower star omega y tensor ox of L abuts to hi plus j on y with coefficients in omega y tensor the pullback of L. And now all these terms vanish except for the j equals 0 term. So the spectral sequence degenerates to to hi on x of mu lower star omega y tensor ox of L is equal to hi on y of omega y tensor the pullback, which is 0 by our previous step, and so this is 0. But by our canonical singularities observation, this is just omega x tensor ox of L. And so we have Kawamata-Viehweg vanishing for the cell big enough. And here, of course, I is greater than 0, as in our previous step. Okay, and now from there, the next version is just the same thing as we did in the first step. So Kawamata-Viehweg 3, which was just take x comma delta simple normal crossings with a boundary whose round down is 0, and let L be equivalent to m plus delta, where m is big enough. So then by the key proposition from earlier in class, there exists some p from z to x, flat finite with z smooth, and the cohomology of ox minus L being a summand of the cohomology on z of oz minus pullback of m. But now p upper star m is big enough because the pullback of a big enough by a finite map. And so this is 0 for I less than n. And so that gives us Kawamata-Viehweg vanishing for big NF plus boundary, which was KV3. Okay, so I'll stop there for today. So what we have left is going to the singular case. So now the last step is going to the KLT case. And the argument there is the same argument here, where we had to use this Leray spectral sequence and vanishing for this log resolution, except now our log resolution is of our KLT pair rather than of our smooth X with effective divisor n, as in this step. But it's the same idea. Now we take a log resolution of x comma delta, but now we need to run the same argument using this Leray spectral sequence lemma to get an analog of Grauer-Riemann-Schneider vanishing for omega y plus boundary. because now we're going to have a KLT pair, so we're going to have a boundary there, while in this step we didn't have a boundary. So on the way, so basically KV3 implies by the same argument a Grauert-Riemenschneider vanishing where you have a boundary, or you can think of it as a relative version of Kawamata-Viehweg vanishing. And then that will apply to the case of a resolution of a KLT pair to get it for KLT pairs. So that'll be Wednesday.